Hello, everyone. Today, let's try out some exam-style questions related to pH calculation of weak acid and bases. So talking about pH calculation, everybody knows that we are usually using this formula, which is pH is equal to minus log the concentration of the hydrogen ion. So for example, if I have the hydrochloric acid, which is a strong acid, of concentration 0.1 mole decimeter cube. And its pH is just simply, we can just derive this 0.1 into our formula. So the pH of the HCl would be minus log 0.1, and it should be eventually equal to 1. This formula shows that the pH value of acid is actually related to the hydrogen ion concentration in the solution. But it's actually the same for weak acids and bases. But the application is slightly more difficult. Let's have a look at this question. So this is actually from past paper. A saturated aqueous hydrogen sulfide has a concentration of 0.1 mole decimeter cube. And then a pH of 4.0, demonstrate whether this is a strong or weak acid. So let's assume that if it's a strong acid, or if we try to calculate the pH from the concentration of this hydrogen sulfide, and then you should notice that this actually should be the same as HCl, but the pH is 4 instead of 1. So this shows that this is a higher pH, indicating this is supposed to be a weaker acid. So the answer for this question is simple, is that it's a weak acid. But why so? Why a weak acid doesn't have the pH value of 1 in this case? So this is actually because whenever we talk about strong acid, the acid concentration will be equal to the hydrogen ion concentration in strong acid. Because remember, how do we define strong and weak? Strong means it fully dissociates. That means if I have HCl and it dissolves in water and dissociate, you will get some hydrogen ions and the chloride ions in aqueous form, both of them. So if our hydrogen chloride have the concentration of 0.1, and then the hydrogen and chloride ion should both have 0.1, concentration of 0.1, because they fully dissociate. However, that's not the case for weak acid. Many students does not really understand what does that mean by partially dissociate. That means let's try the ethanolic acid. This is classic. So since it partially dissociated, there will be equilibrium established between the dissociation of the weak acid. So we've got CH3COO- as this ion, and also our hydrogen plus. But in this case, if I have 0.1, the acid before dissociation, but after the whole system reached equilibrium, the concentration of H is definitely much smaller than 0.1. There could be 0.01 or even smaller, or 0.001, and it would be the same for another ion. Because they dissociate, that means you break apart this molecule at the same time. So this is why whenever you calculate the pH of the weak acid, essentially you're still trying to figure out the pH using the concentration of H+, which is this case, this very small number. So whenever in this question it tell you the concentration of the acid is 0.1, you cannot directly derive this into the formula anymore because they are not equal to each other. Okay. So if we deduce, we can deduce back the concentration of the hydrogen ion in this acid because we know the pH. So since pH is equal to minus log H plus, so the minus log H plus will be equal to 10 to the minus pH squared. So in this case, and it should be 10 to the minus 4 mole per decimeter cube. So 0.0001 mole per decimeter cube. That's definitely much smaller than 0.1, which also shows that the fact that they partially dissociate. Okay. So let's have a look at a more difficult calculation, which worth 4 marks. Okay. So these two are separate questions, by the way. So calculate the pH using table 15 of the data booklet of the solution of ethylonic acid, so the CH3COOH, and made by dissolving 1.4 gram of the acid in distilled water to make 500 centimeter cube solution. Okay, many students will feel pretty lost for this type of question because there are way too many informations, but we can deduce backwards. So let's have a try again. Just remember, whenever you're asked to calculate the pH, you'll always be using this formula. So now our question is, how do we know the concentration of hydrogen plus? Okay. So since they said they want us to refer to the information in table 15, let's have a look. By the way, because I found this question in the old past papers, so the versions of the mark scheme could be a bit different. But anyway, you're supposed to look at this table of the carboxylic acid, like the Ka and pKa of weak acid and bases. So this table, you find the information about ethylonic acid, and the pKa is equal to the 4.76. I'll write it here first. That's a very important information. Okay, so why we are using the Ka here, or what is Ka exactly? What is Ka? So Ka is not only a number. Remember the equilibrium constant? So we studied equilibrium constant, which is Kc. So Ka is actually the equilibrium constant for acid exclusively. A stands for acid. Remember, we said since the weak acid partially dissociates, so there is equilibrium establishing between them. So in this case, the Ka expression will be exactly like Kc. It will be the concentration of the product, which is CH3COO minus, and times the concentration of the reactant, so which is CH3COOH, which is the acid concentration. Okay. So as we mentioned before, whenever an acid dissociates, the concentration or the dissociation amount of these two ions are the same because one molecule dissociates and produces two of these at the same time. So we can say that these two actually equal to each other, isn't it? So now we can simplify this equation into H plus square, since they are the same, and CH3COOH. Okay. Now you may be wondering, why am I bringing this whole thing up here? So now let's come back to the equation. We want to find the concentration of hydrogen in this case with the help of Ka. So now we got the expression of Ka, which involves our H+, that's what we want to find here. So our H+ is essentially equal to, if we do some math, it will be like Ka times the concentration of the CH3COOH in this case. Yeah. So now we are pretty much reaching the right answer already. The rest is that we need to do some little calculation by ourselves. Because once you got the concentration for H, and the next step is you derive it in, and you got your pH, okay? You are more than halfway through. But now, let's try to derive the number in. That's kind of tricky sometimes. So first of all, what is the value of Ka? The value we got from the data booklet is pKa is 4.76. If you didn't know, pH is minus log H+, and pKa is actually minus log Ka. So this means Ka would be equal to 10 to the power of minus pKa. Yeah. So in this case, would be 10 to the power of minus 4.76. That's the value of Ka. Okay. We got one of the value here already. And then last one is the concentration for the ethylenic acid. Okay. So here they mentioned that they made a solution of ethylenic acid by dissolving 1.4 grams of the ethylenic acid in distilled water. Here the thing is that whenever we mention the concentration, it has to be in mole per dm cube. So 1.4 grams, we need to convert it into mole first, and then divide it by the volume of the solution. So the acid concentration calculation would be 1.40 divided by the MR of the ethylenic acid, which is supposed to be 60. Okay, 60, that's the mole concentration, and then you divide it by 500 cm3, but it has to be in mole decimeter cube. So we need to convert the cm3 into dm3, which is 0.5 dm cube. Okay, so now we derive everything into the equation. We should get a final answer of, should be approximately 9.005 times 10 to the power 4 mole per dm cube. Whoops, sorry. Mole per dm cube. Okay. And now we derive this answer into our original pH calculation equation. And the pH is supposed to be minus log, should be 3.045, like 0.5, this value. This is the value that making lots of sense because ethylenic acid is a weak acid. So it's definitely having a pH higher than 1. So in this type of calculation, if you got an answer that's even lower than 1 or like lower than the strong acid, then definitely means that you're wrong. Okay. And the last of all is that this is a question for me to ask you guys to think about it by yourself, is how do we apply the same to a weak base such as ammonia? Noted that for weak bases, there's also equilibrium exists. So, which means ammonia dissolve in water and they should form the ammonium ion with the OH ion. But then if you want to calculate the pH of it, you still need to look for the concentration for H+. So now you need to consider the value of Kw, also the value of the OH minus, so the hydroxide ion. Think about it and try out yourself. That's it for today.